In the previous class, we discussed about basics of vector calculus, and then we started discussing about electric field and some related phenomena and their relations. So in particular, we looked at what is called the electric field intensity. Then we also looked at the electric displacement density, and we also saw something called conduction current density, and we related the conduction current density to the electric field, and in fact that relation is nothing but another form of Ohm's law, but without using voltage and currents. So since we are now talking of any general medium which need not be bounded, the more appropriate way to deal with the phenomena in such cases or in such media would be to make use of the fields rather than voltage and current. So since we discussed about electric field last time, today let us look at magnetic field. So the electric field and magnetic field have a common point of origin. That is, both are interrelated in the sense that the cause for both electric and magnetic fields is a charge. So the electric charge is nothing but what is the cause behind both of these phenomena. So the only difference is static charge causes electric field and moving charges cause magnetic field. Now this should not come as a surprise. So you know that a current carrying conductor always produces a magnetic field around it. So this magnetic field phenomena was studied by many scientists, and a relation was developed to show the effect of a small current element rather than showing the effect of the full conductor. The effect of a small current element, let us say the current I flowing over a length dl, where the dl vector is pointed upwards due to the current. So at a distance of r from this current element, the magnetic field intensity, so just like electric field intensity was represented as using the symbol E, the magnetic field intensity is represented using H. But since we are talking of the effect of a small current element, we are writing the magnetic field as BH, and that is nothing but the current I, which is not a vector, now r cap is the unit vector along the radius or the axis, the radial distance away from the current element, divided by 4 pi r square. So what you see is that there is a vector product of the length element and the distance element. So let us now try to see what is the direction of the dh. So the length vector is oriented upwards. Now, without losing generality, assume that this current element and this point at which we are trying to measure the magnetic field, they both lie on the plane of this piece of paper, the paper on which I am writing. So if the current element and this point, they are both on this piece of paper or the plane of the paper, then since we are taking the vector product of dl and r, the direction of the magnetic field at this point will be given using the right hand thumb rule. So take your right hand and point the curled fingers from the length vector to the radius vector. So the length vector is upwards, radius vector is this way. So my fingers, curled fingers, will essentially move clockwise from dl to r. But which way is my thumb pointing? When I am curling my fingers in this way, my thumb is pointing downwards. So therefore, the magnetic field vector dh will be going into the plane of the paper. So this notation of a vector going into the plane of paper is shown this way. So new notations. This means vector going into the plane of the paper, and this means vector coming out of the plane of the paper. So a very easy way to remember this is to think of an arrow coming towards you. So an arrow coming towards you would probably look like a point, and an arrow going away from you would look like this because of the end of the arrow. You can think of an arrow looking like this. The arrow that is actually used as a weapon. And bigger the radius of these circles, more is the magnitude. Smaller is the size of the circles, smaller is the magnitude of the vector. So this is something that we use. Now, using right hand thumb rule, we can get the direction of magnetic field. You can also look at this in a converse way, that if the current direction is towards the top, then the curled right hand fingers point towards the plane of the paper. But since current itself is not a vector, let us not use this notation. Let us not use this convention. Let us only look at vector quantities. So I is not a vector, but IdL is essentially the direction of current manifested in the direction of length. So immediately what we can see is that this magnetic field is independent of the medium parameters because it is dependent on I, dl, pi and r. There is no quantity about the medium parameter which has any effect on h. So this dh is medium independent. So if I want to see the magnetic field as a function of the medium parameters, we define something called as magnetic, this is called so this law, this relation is also called as the Biot-Savart law. Now if I want to see the medium driven magnetic field, I define a new quantity called magnetic flux density, or B. This is nothing but mu times H, where mu is the permeability of the medium. So the permeability of a medium, just like how we define permittivity. So let us write this. Let us see what this is. The unit of permeability is Henry per meter. So we just established that B is nothing but mu times H. So if mu becomes higher, the B will also become higher. If mu becomes low, B will also become lower. So the permeability of a medium is defined as the ability of a medium to support the magnetic field formation inside it. Just like permittivity was a measure of resistance, permeability is a measure of the ability or how much it allows the supporting of a magnetic field inside it, the medium. So in our discussion in the previous class and this class, we established four broad quantities. For electric and magnetic fields, we established four basic quantities. So we established that if the electric field is vector E, then the electric displacement density D is nothing but epsilon times E. And if the magnetic field is H, then the magnetic flux density B is nothing but mu times H. So in some sense, we can see that these two relations look very similar. The only difference is the electric field E is dependent on the medium and D is independent of the medium. And here it's the opposite. H is independent of the medium and B is dependent on the medium. So in some sense, B shows you the flux lines in the medium. Now, if we look at the units of permittivity, it is nothing but farad per meter. If you look at the units of mu, it is Henry per meter. If you look at the units of electric field, it is volt per meter. Whereas if you look at the unit of magnetic field, it is ampere per meter. So this shows us something which is intuitively very interesting. we are dealing with volts and here we are dealing with amperes. Here we are dealing with capacitance in farads, here we are dealing with inductors in henries. So in some sense, or not just in some sense, in a very intuitively and important sense, the electric field and magnetic field are related. And why not? We just mentioned that the electric field and magnetic field have a common cause. Electric field is caused due to stationary charges and magnetic field is caused due to moving charges or current. And the basis for both is a charge. So therefore, the electric and magnetic fields are related. And this phenomena was essentially observed by many scientists, especially in the 19th century. So just to name a few, you have Gauss, who looked at electric and magnetic fields both from a different standpoint, from different perspectives. You have Ampere, who studied the relationship between magnetic field or how the current carrying conductor produces magnetic field. You have this person called Biot who made this relation for magnetic field as a function of current and distance and length of the conductor. We have Michael Faraday, who proved that a time varying magnetic field could actually induce an EMF, which is the principle for modern day generators. We also have James Clerk Maxwell, who looked at electric and magnetic fields and how to correlate them. And we have Heinrich Hertz, yes, the same Hertz after whom the unit of frequency is named. Heinrich Hertz actually showed experimental demonstrations of how the electric and magnetic fields are very closely related to each other. So now, before we discuss this dependency in more detail, let us look at these two equations, this one and this one, in more detail. So what we can see here is that the quantity permittivity epsilon and the permeability mu, they are essentially something like a constant of proportionality which relate dE and BH. So it is like saying, if I have a vector E, and let us say if epsilon is below 1, then where will be the direction of D? The D will be something like this. Same over here. If I have a magnetic field H and mu is less than 1, then B will be something like this. Now just like epsilon, mu is also mu 0, mu r, where mu 0 is the absolute permeability of free space and mu r is the relative permeability of the medium. So you already know the value of mu 0. So it seems that in general, when epsilon and mu are real quantities and whatever be the value, you will see that the direction of D and E in case of electric field and the direction of B and H in the case of magnetic field are the same. So what's the big deal? The big deal is that the medium where epsilon and mu are real is called an isotropic medium. So in such case, the electric field vector and the displacement density vector will be the same. Likewise, the magnetic field vector and the magnetic flux vector will also be the same direction, not magnitude. So I can also say isotropic medium is a medium having direction independent properties. That means the direction of the field or the direction of the flux is governed by the direction of the field. Likewise, the direction of the displacement density is governed by the direction of the field. The medium plays no role in the direction. So the medium is direction independent. However, there are media which are direction dependent, and those are called as anisotropic medium. Which means that if my electric field vector is E, it may be possible that my D can look like this also. Or if my magnetic field vector is H, my B can look like this also. Now this is called an isotropic medium. So now the relationship, suppose I am writing the relationship for the electric field and the flux density. Now in such case, the representation of epsilon is not so easy, because the directions of epsilon and D are now not the same. So if D is a vector having this kind of component, and the electric field vector E looks something like this. So since both D and E are vectors, epsilon cannot be a vector, no matter whether it is isotropic medium or anisotropic. So what essentially happens is that we write this relation in the form of a matrix. So we say the dx, dy and dz components are related to the ex, ey and ez components, where this matrix, which I have not yet filled, denotes epsilon. So this is a 3x1 matrix, this is also a 3x1 matrix. So therefore this should be a 3x3 matrix, where we are writing the different components of epsilon using the components of each x, y and z parts as functions of x, y and z axis respectively. So I can say the x vector or the x component of epsilon can be written further as three quantities: dependence on x, dependence on y, dependence on z. Likewise, the y component can be written as and this way. Now, rather than a single number, the epsilon is represented in the form of a matrix. Now this kind of representation is called as a tensor. And now epsilon is written as this way, epsilon with double bar. or mu with double R. These are called as tensors, which have to be represented in the form of a matrix, not a number. So this is a brief idea of isotropic and anisotropic medium. The discussion about anisotropic media is beyond the scope of this course, but there are a lot of media like that. So now, having established these basics, let us now delve a little bit into the basic laws which govern electric and magnetic fields. So the first law that we will see is the Gauss's law for electric displacement. So the Gauss's law for electric displacement states that the total outward electric displacement through a closed surface equals the total charge enclosed by that surface. So in words, that is this. Now, does this sound familiar? Yes, because A, you have already studied this Gauss's law in your high school physics, and also because this statement sounds very similar to something we looked at in the last class, and that is nothing but the divergence theorem. So I had briefly mentioned that the divergence theorem, which was also proposed by Gauss, gave way to this Gauss's law for electric displacement. So if this is my closed surface and there is some charge Q, then the net outward displacement, so D is what? Displacement density. This is not a displacement. So what is this? D, we proved, is nothing but Q by 4 pi r square in magnitude. So it is like saying whatever is the charge that is inside is sort of distributed along a surface area, because the denominator is indicative of surface area. So this is like saying so therefore the total displacement is nothing but the displacement density integrated over the whole surface area. So therefore I will say total outward. Why outward? Because let us assume that the field lines are coming out. So if this displacement density is d, this is nothing but the area integral of d over the whole surface. And what Gauss is saying is that this total outward displacement should be equal to the net charge that is inside the surface, which is q. Now, so far it's okay. So far it's okay. But what we do not know about the charge q is that it could be a single point charge or it could be a group of charges. So therefore, q can be represented as either point charge or distributed charge. So therefore, let us define something called as rho, which is nothing but charge density, which is defined as total charge divided by volume of distribution. So therefore, rho is also called as volume charge density. So the unit for this will be coulomb per meter cube. So therefore, if the total displacement we found out is equal to the charge, then I can write the charge, total charge q, as nothing but the volume integral of this charge density over volume. Now charge is a scalar, charge density and volume are also scalars, so therefore this is a scalar quantity. So applying the Gauss's theorem or the Gauss's law, the right hand side can be represented using this volume integral. So therefore Gauss's law becomes something like this. So again, we are seeing that we are correlating a double integral with a triple integral, and that in some sense indicates the use of the divergence theorem. So now using the divergence theorem, I can say that this first integral is nothing but the volume integral of the divergence of the displacement density vector over volume. So therefore these two are equal. So therefore I can say that the rho quantity will be equal to the divergence of the displacement density vector. So what this proves is that divergence of the displacement density is nothing but the charge density. This is called, the first one is called the integral form of Gauss's law for electric displacement, and this is called as the differential form. Why differential? Because you have a derivative over here. the gradient. So this is causing a divergence, which is also indicative of derivative of a vector. So therefore this is Gauss's law of electric field, but we are writing them in two forms. So now Gauss had also proposed a law for magnetic flux. So the second basic law is Gauss's law So Gauss said, and the way he said it, it is almost analogous to what we have explained for electric displacement. Gauss said the total magnetic field, or sorry, the total magnetic flux coming out of a closed surface is equal to the total magnetic charge or poles enclosed by the surface. So it states the total outward magnetic flux through a closed surface equals the total magnetic charge. For magnetic, we don't call charge, we call it poles, enclosed by the surface. So just like electric flux or electric displacement we were talking about, this Q can now be thought of as a magnetic charge collection. But magnetic charge always comes in pairs. You cannot have monopoles. Magnetic charges always exist as dipoles. So therefore, the net charge inside any closed surface will always be zero, because you have equal number of north poles and equal number of south poles. So in such a scenario, if I say the magnetic flux density B and the total flux is given as this, very similar to what we did for D. So this will be equal to total enclosed magnetic poles, which is nothing but 0. So therefore what we see, the area integral of the flux, that is 0. Now if I apply the divergence theorem, I can also say, if I convert this into a triple integral, this will be divergence of the B vector, and that will also be 0. So what this means is, if you have a Gaussian closed surface and you have magnetic charges enclosed inside having equal number of north and south poles, the field lines may be coming out like this. That is, they are diverging from one side, but they will definitely converge from the other side, which makes the net divergence 0. Even though if you look at one part of the surface, it may appear that the divergence is non-zero, but Gauss's law is defined for a closed surface. So the magnetic field lines will, even if they diverge from one side, they will always come back from the other side. So therefore this makes the net divergence as 0. That is the beauty of it. So in case of Gauss's law for both electric and magnetic fields, the nature looks very similar. There we had described that the divergence of D will be equal to the charge enclosed. In case of magnetic field also, it equals the charge enclosed, except that the charge enclosed is 0. Or I should say net charge enclosed. So this is called as integral form, and this is the differential form. Now, let us look at the third law. The third law is something you are also well familiar with, and that is Faraday's law of electromagnetic induction, which says that the net electromotive force in a closed loop equals the rate of change of magnetic flux enclosed by the loop. Electromotive force means EMF. So therefore, in other words, you can also say that if there's a time varying magnetic field passing through the surface enclosed by a closed loop, some EMF will be induced in the loop because of the time varying magnetic field. So to state this, the net EMF or electromotive force in a closed loop equals the rate of change of magnetic flux enclosed by the loop. So electromotive force is nothing but the potential. So the potential, which is the EMF, as you know, since there is no question of external electric field right now, the only external thing is the magnetic flux. That is nothing but the integral of the electric field over the length of the closed loop in a closed contour. And that is nothing but the change of the net magnetic flux. If you recall, the net flux is denoted as phi. Rate of change of flux means now the phi will be differentiated with respect to time in the form of a partial derivative, because phi can be the function of x, y, z and time, because now the nature of the magnetic flux has to be such that it has to be time varying. Otherwise, there will be no EMF induced. Also, there will be a minus sign because of something called as Lenz's law. The nature of the EMF is such that it is always opposing the cause that is producing it. In this case, it is the magnetic flux. So flux is nothing but the integral of the flux density over area. So I can substitute flux over here. So now I am seeing one equation which is like this. So here, since the dot product is with the area vector which is independent of time, I can take the time partial derivative inside the integral also. Now what I am seeing is that my left hand side has a single integral and my right hand side has a double integral. So therefore I can relate the two using Stokes theorem. So this one can be written using the curl of the electric field, and this should be equal to this. So that means I can equate these two. I can say that the curl of the electric field intensity is nothing but minus of the rate of change of the magnetic flux density. So this is called the integral form of Faraday's law, and this is called as the differential form of Faraday's law. So now there is one more law. There is one more law, but we shall see this next law in the next class. So today we looked at the basics of magnetic field and magnetic flux density or intensity. We looked at isotropic and anisotropic fields, and from our knowledge of the basics of electric and magnetic fields, we looked at three basic laws, that is the Gauss's law for electric and magnetic fields and also the Faraday's law of induction. And each of these laws, we have represented them in the differential form as well as the integral form using the vector calculus knowledge that we already have gained. Now, in total, there are 4 laws, out of which we have looked at 3. The 4th law we shall look tomorrow, and because that law is rather special, and what is the speciality? We shall see it. So, thank you.